Aerodynamics is the study of the dynamics of gases, focusing on the interaction between a moving object and the atmosphere. While both involve fluid dynamics, a ship and an aircraft move through mediums with a vital physical difference. Water is incompressible, but air is highly compressible. This compressibility means that properties like pressure and density change constantly. In any given volume of air, these factors fluctuate based on the temperature and the space the air occupies. Early aviation adopted nautical terms like rudder, hull, and keelbeam. However, because air compresses under force, an aircraft's reaction to the airflow follows a distinct set of physical rules that differ from those of a ship in water. For an airframe and power plant technician, understanding aerodynamics means connecting an aircraft's performance in flight to the specific forces acting on its structural parts. Safely maintaining complex aircraft requires accounting for the four primary atmospheric variables that govern these forces: pressure, density, temperature, and humidity. These variables dictate operational realities, such as the total aerodynamic lift a wing can generate and the actual horsepower an engine can produce. Because the atmosphere is never at rest, technicians rely on a firm understanding of atmospheric physics and the standardized baselines used to calibrate aircraft systems. We begin with pressure. Atmospheric pressure is the physical force exerted against the Earth's surface by the weight of the air above it. This follows a mathematical relationship where force equals area multiplied by pressure. To calculate the pressure, the total force is divided by the area it covers. To visualize this, we use a standard model, a square-inch column of air stretching from sea level to the edge of the atmosphere. The weight inside this 50-mile-high column is 14.7 pounds. Therefore, standard atmospheric pressure at sea level is 14.7 psi. While psi measures force, aviation and meteorology often express this same value using different units. 14.7 psi is equal to 29.92 inches of mercury, a linear measurement, and 1013.2 hectopascals or millibars, the unit nearly universal in modern meteorology. As an aircraft ascends, the column of air above it becomes shorter. With less weight pressing down from above, atmospheric pressure drops rapidly. This chart plots that decrease. The relationship between altitude and pressure is nonlinear, showing a steep drop-off in the lower atmosphere. By the time an aircraft reaches 50,000 feet, the atmospheric pressure has dropped to nearly 1/10 of its value at sea level. This rapid loss of pressure changes how air flows over the airframe and reduces the total horsepower the engine is capable of generating. Temperature also changes with altitude, shifting predictably alongside these pressure drops. The atmosphere is organized into vertical layers based on temperature. The lowest layer, the troposphere, extends from the surface to 38,000 feet. Most civilian aviation occurs entirely within it. Tracing the line through the troposphere shows temperature steadily decreasing as altitude increases. In this layer, the lapse rate is constant. Temperature drops approximately 2 degrees Celsius, or 3.5 degrees Fahrenheit, for every 1,000 feet of climb. This cooling continues until reaching the upper boundary of the layer, the tropopause. At the tropopause, the steady cooling stops and the temperature stabilizes at a constant -57 degrees Celsius. Above this boundary is the stratosphere, where temperatures rise again. High-altitude civilian and military flights operate here, above the weather systems of the troposphere. Understanding these thermal gradients allows engineers to anticipate material stresses on the airframe and calculate how air density will change during flight. Density is the weight of air per unit of volume. It is the primary factor determining aerodynamic resistance and the lift an aircraft can generate. Two rules govern this property. First, density varies in proportion with pressure. Higher pressure packs more air particles into the same volume. Second, density varies inversely with temperature. As air heats, particles spread out, making hot air less dense than cool air. Humidity, the amount of water vapor in the air, adds a third variable. Because hotter air can absorb more moisture, humidity and temperature are closely linked. Absolute humidity is the actual weight of water vapor in a specific volume of air. Relative humidity is the ratio of moisture currently in the air compared to what it could hold if fully saturated. There is a common misconception that humid air is denser because water feels heavy. The physics of displacement prove the opposite. When water vapor enters an air mass, lighter H2O molecules displace the heavier nitrogen and oxygen of dry air. Molecularly, water vapor weighs only 5/8 as much as dry air. By displacing heavier molecules, damp air becomes less dense than dry air. This creates a significant performance penalty on hot, humid days at high altitudes. The resulting low-density air provides less lift and contains less total oxygen for the engine to burn, requiring a much longer runway for takeoff. In the real physical world, the atmosphere is never at rest. Pressure, temperature, and density are constantly changing. To compare aircraft performance and calibrate instruments like altimeters, the industry requires a static, universally agreed-upon baseline. This baseline is the International Standard Atmosphere, or ISA, a mathematical model used by regulatory bodies worldwide. This table freezes atmospheric variables into a predictable chart. The sea level row establishes the standard, 15 degrees Celsius and 14.67 psi. Moving down, the temperature column follows the 2 degree per 1,000-foot lapse rate. The density column shows that as altitude increases, air grows measurably thinner. This standard table is the foundation for theoretical calculations and ensures instrumentation parity across all civilian and military aviation. For a technician, recognizing that flight is governed by these proven physical laws is the first step in safely maintaining modern aircraft for flight.